Good morning, afternoon, evening, whatever time zone you're watching this in. And thank you for attending this presentation. I would also like to thank Pat Lynette and the rest of the not so local organizing committee for the virtual ICCE. Thank you for all of the work you did to make this event possible in light of the COVID-19 pandemic. And I'm really looking forward to an excellent week of presentations and discussions. So thank you very much. The title of my talk is called Physical Model Investigation of Modest Thickness Mangrove Forest Effects on Flow Hydrodynamics, Pressures, and Loads in the Built Environment. I'll be sharing some results from experiments that we performed in the spring of 2019. And I'd also like to acknowledge my co-authors. As a brief outline of what I'll be talking about today, I don't think there's a huge need to motivate this subject, but I'll also share the experimental design and setup and talking about some of the results we found when we added mangroves compared to our baseline condition with no mangroves. And then I'll share some brief conclusions and talk about some of our future and ongoing work. The motivation for this study comes from Hurricane Irma, which affected the Caribbean and Florida Keys in 2017, in September of 2017. 1 month after the storm, we performed damage assessments for 262 waterfront structures in Key West and Big Pine Key, Florida. And something that really jumped out at us during the field study was the parcel scale, so house by house variation in shoreline type. For example, we had houses that had sandy beaches, mangrove shorelines, revetments, or bulkheads. And while we were doing our assessment of hazard intensity measure and how that impacted the damage state, this is the figure you can see with our hazard intensity measure as a freeboard, or the elevation of the wave crest above the lowest horizontal structural member plotted on the x-axis, and the damage state of the structure that we assessed in the field plotted on the y-axis. And we really didn't see any relationships between increasing hazard intensity and increasing damage until we broke out the structures by their shoreline archetype. And what we found was that structures that had mangrove shorelines had lower damage states despite having higher hazard intensity measures. And so this was really interesting because it was similar to reports of mangrove protection during tsunamis and other storms, but previous studies have documented this protection occurring over kilometers of mangrove forests, and we were observing similar benefits over about 50 meters of mangrove between the shoreline and a parcel owner's structure. So this gave us the question of how much mangroves, how much cross-shore forest thickness do you need to provide a noticeable benefit in terms of wave mitigation and load reduction? In order to answer this question, we decided to create a 1 to 16 physical model. But before we created our physical model, we actually went back into the field to measure mangrove prop root densities, prop root diameters, and elasticity. Those data, together with parameterizations provided into the literature, for example, from Ohira et al. 2013, informed our physical model, which we created out of PVC for the trunks and galvanized steel wire for the roots. Here you can see a photograph of the mangroves installed in the wave basin, fronting idealized structural elements. These experiments were part of a larger experimental campaign that investigated macro roughness, seawalls, debris, vegetation, and other tests that were conducted at Oregon State University. One of the really fun parts about this experiment, the really cool parts about working on it, was that there was a really novel experimental setup. You can see our test section was 10 meters wide in the middle of the directional wave basin. On either side, we constructed breakwaters or wave dissipating structures, and we installed recirculating pumps on either side of the basin so that we could generate a continuous current, a continuous and steady current during wave generation. So this allowed us to create wave conditions with and without a recirculating trailing current. Here you can see a plan and profile view of the experimental setup. As you can see, the waves propagated from the wave maker towards the mangroves, and they either propagated through 8 rows of mangroves or 4 rows of mangroves, or 0 rows of mangroves, which made up our 3 experimental configurations. The prototype scale cross-shore thicknesses were 8.2 meters and 19 meters for the M4 and M8 configurations respectively. So we were intentionally limiting the cross-shore thickness to determine if these small-scale parcel cross-shore thicknesses that we observed in the Florida Keys could create significant load reduction. Here you can see a photograph of the instrumentation that we considered. We used acoustic Doppler velocimeters to measure water velocity, US ultrasonic wave gauges and wire resistance wave gauges to measure water surface elevation, and inline load cells and 6 degree of freedom load cells, as well as pressure gauges to measure loads on shielded and unshielded structures. We considered irregular and transient wave conditions or tsunami-like wave conditions. For this talk, I'm going to focus on the tsunami-like wave conditions. We considered 3 different conditions which varied the amplitude and the representative period. As we increased the wave representative timescale, we decreased the wave amplitude. So ERF1 has the longest wave representative time scale and the smallest amplitude, while ERF3 has the largest wave amplitude and the smallest representative time scale. We repeated these trials with and without a current. And so we had conditions with a trailing background current and with no trailing background current. Here you'll see a video of one of the waves interacting with the structures. It happened pretty quickly, but what I wanted you to notice was that as the wave impacted the structure, let me start it over. You'll notice the splash up that occurs on the silver boxes versus the unshielded red structural elements to the right. You can clearly see that there's a reduction in splash up on the shielded structures that is caused by the mangrove specimens. And this was consistent for all of the trials. We considered a quantified measurement of the mangrove effects on the water surface elevation behind the mangroves. Here we're considering water surface elevations measured at US wave gauge 5, which was located in front of one of the side streets directly behind the mangroves. The black lines indicate the M0 configuration, while the blue dashed lines and the orange lines indicate the M4 and M8 configurations respectively. The top row indicates trials run over still water, while the bottom row indicates trials run in the presence of a background current. And what we noticed was that water levels increased behind the mangroves for all conditions, but there is not really a big difference between the M4 and the M8 configuration. So really not too much difference once you added mangroves to adding more mangroves. We saw a similar effect when we considered the water velocity behind the mangroves as well. The peak velocities decreased more quickly for both the M4 and M8 configuration compared to our baseline case. However, we don't see a huge difference in the velocity time series comparing the M4 and M8 configurations. We also measured the loads considering the 6 degree of freedom load cell, which is shown as the bold box in the upper right-hand corner. The left side figure plots the wave representative time scale on the x-axis and the force measured by the 6 degree of freedom load cell on the y-axis. The shaded symbols indicate trials run in the presence of a background current, while the hollow symbols indicate trials run over still water. And you can see that as we increase the wave representative timescale, the force decreased. This may also have to do with the fact that we reduced the wave amplitude as we increased the wave timescale. But we also noticed that in all cases, the force decreased as we moved from the M0 to the M4 to the M8 configuration. Another way that we looked at this was looking at the cross-shore distance of the mangroves. So we consider the cross-shore distance of the mangroves on the x-axis, and the force again was plotted on the y-axis. And each wave trial is represented as a different symbol. And you can see that for each case, the wave force on the inland structure decreases as we move from 0 mangroves to 4 mangroves to 8 mangroves. However, it's a nonlinear effect. So as you move from 0 to 4 mangroves, you see a different reduction than you do as you move from 4 to 8 rows of mangroves. We investigated this in more detail and considered relationships between incident wave representative timescale, salinity, water depth, as well as the cross-shore thickness of the mangroves. And we found a relationship between the percent reduction in inland force on the inland structure and the mangrove cross-shore thickness divided by the wave representative timescale and offshore wave celerity. And you can see this figure plotted here for all of the wave conditions we trialed with, again, black circles indicate ERF1, our longest wave period and lowest amplitude. Blue triangles, ERF2, and orange squares indicate ERF3. Again, hollow symbols indicate trials run over no background current, while shaded symbols indicate that trials did have that background current. And I think this is really important because it starts to show a relationship between how much mangroves you need, considering your wave representative period, normal and offshore celerity. Something also that was of note, so if you have a larger wave period, you need more cross-shore thickness of mangroves in order to protect your structure. Another thing that we noted, though, was that the mangroves considered here really made up less than 10% of the quantity of the representative timescale times the wave celerity. So we saw that mangroves are having an effect even at very small cross-shore thicknesses compared to the wave period and celerity. In conclusion, I think is really exciting to show the potential of natural and nature-based infrastructure as a coastal protection mechanism. And I think, especially considering sea level rise and increasing coastal flooding hazards, it's important that we develop these resilient and sustainable solutions. I hope that we can come up with a standardized guidance for the successful implementation of mangroves and other natural and nature-based implementation in coordination with traditional engineering structures, which I think are also a very important way to protect our coastlines. I'm very excited about some of the future work that we have going on. We're looking at large-scale tests, collaborating with the US Army Corps of Engineers and Oregon State University at 1-to-1 scale and 1-to-2 scale to compare scaling effects moving from 1-to-16 to 1-to-2 to 1-to-1, as well as looking at some exciting field work of boat wakes and wind wave attenuation through mangroves. With that, I would like to once again thank the conference organizers, as well as our funding sources and the wonderful folks that we've collaborated with during these experiments. Thank you very much.